All right. In this video, I'll give you the introduction of operators. Now, operators are basically they are a means to calculate out the expectation values. If we go back to the wave function psi is a e to the power of I kx minus omega t, where this k is a propagation vector and its value is it's 2 pi by lambda, and we know that h bar k comes out to be momentum. Now, if I take a partial derivative of this wave function, if I take the partial derivative of this wave function with respect to x, what will I get? I will get iota k and a e to the power of I kx minus omega t. Now, this is wave function, therefore del psi upon del x will be iota k psi. You can see that this k can be replaced by momentum by h bar. So I will write here momentum by h bar iota psi is partial derivative of psi with respect to x. So we can write here p psi is minus iota h bar del psi by del x. Now, the point of the fact is that there is always a connection between the dynamical quantity momentum and this partial derivative. This partial derivative multiplied by minus IH bar. So there is a relation, there is a clear connection between this momentum, this dynamical quantity, with this I minus IH bar and partial derivative of psi with respect to x. Now, this thing can be assigned as an operator. So which operator? Because it has a clear relation with the momentum. Therefore, this thing can be represented by an operator known as momentum operator, and for that we use a symbol p caret, or you can say cap. This p caret is minus IH bar dou by dou x. So what does this momentum operator mean now? If we try to give some meaning to this equation, is that when you make use of momentum operator, whatever comes after it, you have to differentiate that with respect to x and multiply the result with minus IH bar and multiply the result with minus IH bar. So here p caret is a momentum operator, and this is equal to minus IH bar del by del x. Now, similarly, we will look for another important operator, which is called as energy operator. Now, if we take the partial derivative of this function with respect to time, we will get minus iota omega psi. As all of you know that h bar omega is equal to E. So what is omega? omega is h bar by E. So I can use this omega here, and I will write del psi upon del t is equal to minus I, it must be E by h bar, minus I E by h bar psi. I can simplify it a little bit more. So I can write like this: E psi is equal to I h bar delta psi by delta t, the partial derivative of psi with respect to time. So in the similar fashion, the dynamical quantity E here has a relation with this operator. Clearly it has a relation with this operator. So that relation, the relation that this energy has with the operator, can be written as E with a caret on it. And that will be what? That will be I h bar partial derivative with respect to time. So here, E caret or our cap on an E, this gives us the energy operator. This gives us the energy operator. Now, what does this energy operator mean? It means anything that will come ahead of it, you have to take its partial derivative with respect to time and multiply that thing with IH bar. Now, if we go to a very general expression that E is the energy, and this total energy is sum of kinetic energy and potential energy in one dimension, for the sake of argument. I will replace this energy equation by virtue of operators. So replacing this equation like that, let us first go with this. E is mv whole square divided by 2m plus v of x. So E can be written as p square by 2m plus v of x, where this p is the momentum of the particle, right? So total energy is the sum of kinetic energy and potential energy. Now I want to replace this equation by virtue of the operators. Now for E I will use E cap. For P I will use P cap square by 2m, plus for V it will remain as Vx. Now I can use the energy operator here. What is energy operator? That is IH bar partial derivative of time is equal to 1 by 2m will be out. Momentum operator, that is h bar by I cap partial derivative with respect to x whole square plus v of x. So this will be I h bar is equal to minus h bar square by 2m del 2 del x2 plus v of x. Now if I put a wave function in every term in this equation, I h bar del by del t psi is minus h bar square by 2m, the double derivative of psi x2 plus v of x psi of x. So what is this? This is Schrodinger's time-dependent wave equation. So we can say that the operators, in this case, momentum operator and energy operator, they are themselves acting as postulates in confirming the Schrodinger's wave equation. I hope you understand this. All right, so we have talked about operators. We talked about momentum operator. We talked about energy operator. Now, these operators can act as means to calculate the expectation values. The reasons for that is that we can replace this momentum by virtue of its operator. Now, if for the sake of argument, if we have to calculate the expectation value of momentum, the expectation value of momentum can be written as psi star p, the operator of momentum, psi dx. The limits will extend from minus infinity to plus infinity. So you can replace the momentum by virtue of its operator and work out the integration from minus infinity to plus infinity. We can calculate the expectation value of momentum. In the similar fashion, the same will be true for energy. Suppose we want to calculate the expectation value of energy. So what that will be equal to? That will be equal to minus infinity to infinity psi star E operator psi dx. So in this equation, all you have to do is to replace this momentum operator by its value. What's that? That is h bar by I delta by delta x. In this case, the energy operator has to be used, and energy operator is it is I h bar del by del t. Now, the most important question that arises in our mind at this stage is that why this is a special place for the operator. Why operator is not placed at the extreme of the at the extreme of this configuration? Why it is not on the left side, or why it is not on the right side? So in order to get this clear, if for the sake of an argument, if I say that the expectation value of momentum is a line integral from minus infinity to infinity p operator psi star psi dx. Now, if we closely look in this configuration, we see that this psi star and psi, they will both become zero at infinity. Psi star and psi, they will both become zero at plus minus infinity. So placing the operator to the extreme left of this configuration is not the right choice. Similarly, if we take this operator on the extreme right, we write this operator here, so here it will be dx. So what will come out of it? It will be minus infinity to infinity psi star psi h bar by I partial derivative of x dx. You see this equation? Okay, you will get something that is not in itself something right. Minus infinity to infinity, psi star, psi, h bar by I. So this is meaningless. It doesn't have any meaning. So the point is that an operator has a right place. You have to make sure that this operator is between these two psis. It has to be between the psi star and psi, right? And the moment we have placed it between psi star and psi, we can calculate the expectation value. So psi star, suppose this is a momentum operator, that is h bar by I psi dx. Now this thing can be evaluated. On evaluating this thing, we will be in a position to calculate the expectation value of momentum, and the same thing is true for the energy.